I am Paep. I am allegedly giving a talk about the crypto acceleration stuff in FreeBSD. In the real world, I'm usually an embedded sort of person who rarely ventures out of the kernel. So I'll talk to you about where we find crypto stuff in FreeBSD and how we abstract all this using the Open Crypto framework we borrowed from OpenBSD a couple of years ago. Then I'll tell you about how crypto acceleration works and when you might not want to use crypto acceleration. And I'll show you some numbers about when it works and when it doesn't work. And then maybe I'll have some ideas and maybe people want to follow these ideas and do useful things for us. So there's lots of cryptography in FreeBSD because we're all very paranoid people. In userland, most of our applications which we ship with the base system use OpenSSL. The usual suspects which everyone knows are things like SSH and Friends, and then there's also all the Kerberos things, which all happen to like crypto. If you're into the course tree, certain GNU-ish applications will start to use GNU-TLS, which is the GNU answer to the license of OpenSSL. And then there's a couple of applications which insist on reinventing the wheel and implementing certain cryptographic algorithms themselves. HostAPD, which is in the base system, used to be one of those, but recently it's started using OpenSSL. What some people don't know is that there's also cryptography in the kernel. The greatest subject is IPsec, which uses quite a lot of cryptography, and it likes in being fast as well. We've also got some block devices which use encryption. We've got two sets of block device encryption systems. We've got GDEE, which was the old one which Paul Henning wrote originally a couple of years ago. And then Pavel wrote Jelly, or G-E-L-I, I don't know how people want to pronounce this, which also uses, well, influent block device encryption. And ZFS uses encryption independently, and it's, well, I don't know how it encrypts, but it's not a block device encryption thing. One of the problems with cryptography is that it's lots and lots of mathematics, lots of little numbers getting added, divided, shifted, and transformed in many meaningful and interesting ways. And that will hog your CPU for a long time for every transaction. This is a problem if you're a busy web server and you're selling a million products at a time and a million people are clicking the please buy button and all these transactions are happening. You can't parallelize it very easily because, well, you're hitting memory and you don't want to do this. And lots of scary code duplication is also not a very good idea. So cryptography turns out not to be very easy. A couple of years ago, in 2002, as a matter of fact, I discovered this morning, we borrowed the Open Crypto framework from OpenBSD. Sam Leffler originally imported it to provide a consistent hardware and software interface to cryptographic systems. It was mainly intended for IPsec originally, but the OpenB implementation also had supports to export the interface to user space, and they made it fairly modular and extendable, so you could add different algorithms, you could just plug them in, and they would provide the same interface to user space and to kernel subsystems. The Open Crypto framework uses a session-oriented interface, so whether you're in the kernel or in user space, you start a session, and you say, I would like to use this algorithm, this algorithm, this algorithm, this algorithm, and with these key sizes, these key sizes, and these key sizes, and then you pass in a stream and you continue to use the same session. The interface is asynchronous, so you're not going to be blocking on a crypto operation. You'll send the crypto operation off to happen, and then you'll wait for a message to return, hi, I've done it. You can find your encrypted block or your decrypted block, as the case may be, here in memory. The kernel systems who want to use this can just include a header file. Well, it turns out there's more than one header file. That's the main one. And userland has an IOPTL interface, which they can send messages past over the dev crypto device. The nice thing about the Open Crypto framework, which is what this talk is actually supposedly about, is that there are hardware accelerators on the market which will offload crypto for you. So instead of hogging your CPU for many milliseconds at a time on cryptographic transactions, you have this little PCI card sitting there which does nothing other than these transactions. Often they can also do more than one transaction at a time, though I've not seen any hardware that actually does this. It's fairly easy to write device drivers to implement this hardware and register them with OpenCrypto, and that's actually how I got into giving this talk. This summer I made the horrible mistake of finishing off and committing a driver which was written for the crypto block, or the entertainment crypto device in the geode CPU, which is found in Sophos boxes. And as often happens with the FreeBSD project, as soon as you touch something, you own it, or at least partly own it. So, a very bad idea, I can't recommend it. The driver interface is extremely easy. I think the driver was some French gentleman, Patrick, whose last name I can't remember, wrote most of the driver. And it was fairly complete, and the whole driver is not more than a couple of thousand lines of code. You can, as a device driver, allege that you support one or more algorithms. One of the problems is that if you don't support an algorithm, you'll have to somehow provide it in software, which I'll talk a bit more about later. Device drivers have limited support for flow control. You're not allowed to sleep inside these crypto device drivers, but you are allowed to return certain error messages like E-busy or E again to tell your users that they can try again in a minute. One thing to remember is that acceleration can sometimes slow down your things, which is a curious phenomenon. I'll show you some slides later with numbers where this happens. That's actually, if you enable crypto acceleration, things slow down by an order of magnitude. It's probably contrary to expectations. The OpenCrypto framework we've got in FreeBSD currently supports a number of devices. The GLXSB driver I imported supports the crypto block, or entertainment crypto, in the geode processor. This is found in the Sophos boxes, and it's also in other, I think the wrap boards also run on geode these days. There's the hyphen driver, which supports a number of cards. The hyphen has a number of good cards and a number of bad cards. The driver supports both of those. Padlock is a bit like the geodes device. It's found on VIA processors. And SafeNet, I have not seen any of their hardware in the wild, but it supposedly exists. And then there's UBSec, and that's found all over the place. There's many vendors which put Broadcom chips on their PCI cards and put their own brand on them. So if you find a crypto accelerator in the shop, you plug it in, you'll suddenly find, oh look, you have a Broadcom something crypto accelerator sitting in your system. These Broadcom drivers are surprisingly fast. They work really well in my experience. So the crypto bits can be used. Most kernel subsystems already use the crypto code. One exception I found is GBDE. I don't know why it doesn't use the crypto framework, but it just doesn't. So even if you've got a crypto accelerator sitting in your hardware and you're using GBDE for block device encryption, it won't go faster. Or if you're using fast hardware and enabling acceleration, it won't go slower. The Jelly device does use the crypto accelerator or decelerator, so that's nice. In OpenSSL, which is way up in user space somewhere, there's a phenomenon called engine, which can be used to enable hardware cryptography up in user space. It's not used automatically on FreeBSD. Part of the reason is the deceleration phenomenon I've repeated several hundred times today, but there's also some other problems with it, that if OpenCrypto does not have hardware to implement a certain algorithm, it will fall back to software. And if you're context switching continuously for SSL, for crypto transactions, you're going to slow things down. It's much easier to just do these calculations in user space and save on overhead. On the other hand, it's fairly simple to enable applications to use an engine. I have some patches which do it automatically. It's one line in the OpenSSL code if you want it all the time, and if you just want it for SSHD or SSH, it's actually just 2 lines in SSH.c or SSHD.c. These patches are somewhere on freefall if people are interested. And now what you've been waiting for are probably these fascinating performance measurements. There's one OpenSSL application called OpenSSL Speeds, which will test your OpenSSL performance for you. I tested this on a Sophos box, which is a 500 MHz AMD CPU. and I tested it with 128 bytes CBC AES transaction. The top line is the performance with the crypto acceleration disabled, which is, well, it's not fast, but it's not very slow, but it's not very fast either. And then the second line is what happens if you put the cryptodef engine on, and particularly with 1K, 2K, and 8K blocks of data, things go rather fast. It's a pretty nice thing. But I did mention the deceleration problem. Oh, no, I didn't. This is the large file. This is more interesting than just a raw SSL speed test. I created a very large file, or a relatively large file, and encrypted it with OpenSSL. And if I just do it without the engine, it takes about a minute and a half to encrypt this file, which is an insanely long amount of time in software. But if I enable the crypto engine, it suddenly happens in under 20 seconds, which is a bit more acceptable. And then, well, I mentioned the slowdown effect. This is on a fairly fast AMD system. It's a 3.8 gigahertz AMD system. First line is again with the accelerator turned off, and I see that I am measuring real time instead of CPU time. But you see the numbers are just halving, especially, or even factor 5 on the 1K block. It just slows down incredibly. You don't want to enable acceleration on these fast systems. And the large file is even more interesting. If you encrypt this 350 megabyte file on a fast AMD system, it takes about 9 seconds with the accelerator turned off, and about 20 seconds with the accelerator turned on, which is why we call it crypto decelerators. There are a number of things that are still missing in the whole open crypto world. One of the things that's currently bothering me is the code duplication. If a hardware accelerator does not support a certain algorithm, you have to fall back to software. Currently, most accelerators only implement one algorithm. It's usually AES of some description. And some people do like using other algorithms too, like DES is still fairly popular. And you'll have to implement it in software. And there's currently no easy way of reusing the codes to do it in software between drivers. So the via catalog driver implements certain algorithms in software, and then the Geo driver also implements the same algorithms in software again. And there's quite a bit of code duplication there, which is not very nice. Another thing I would like to do is enable the cryptodef engine in OpenSSL by default, but I would like to do it in such a way that if acceleration is going to actually be deceleration and slow things down, the engine won't be used, but I've not found a way to do that reliably yet. I would, also definitely like to find a way of convincing OpenSSL OpenSSH to automatically use the engines. OpenSSH does not ask OpenSSL to please use any engine you may find. So even if you've got engines enabled by default in OpenSSL, OpenSSH won't know about them, and it will still go blindingly slow or blindingly fast depending on whether you're accelerating or decelerating. And it turns out my talk is rather shorter than I had expected, which is usually what happens when I give a talk for the first time. So you can entertain me with questions and remarks for the next, how long is your game, Julian?
80 minutes.
Excellent. You can entertain me for another 80 minutes with questions and remarks. And there's the first question, or remark, or insult.
Hi.
The microphone.
Testing. All right, maybe this mic doesn't work. Maybe it went by too fast, but can you talk a little bit more about the reasons for the deceleration again? I think I might.
Oh, the deceleration. If you've got a really fast CPU, it's it's going to crunch the numbers really fast. But the main problem is that many of these crypto acceleration cards are 32-bit PCI cards. And when you're using a 64-bit CPU and you're, a 64-bit fast CPU, and you've got all these numbers and you're passing them through a 32-bit PCI bus, it's not going to be very happy about this. And then once it's done with this transaction, you're going to fish up your encrypted or decrypted number over this 32-bit bus again. It's again not going to be very happy about this. So you've got two contributing factors. One thing is you've got walk speed. If you've got this multi-gigahertz CPU, which can crunch the numbers much faster than whatever piece of silicon is sitting in this crypto accelerator. And then you've got this tiny 32-bit bus sitting between you and this supposedly faster piece of hardware. It's going to slow things down. It's the usual weakest link phenomenon. Does that answer your question? Adrian also.
Hi. Did you try doing the crypto benchmarks with the CPUs doing something other than doing the encryption?
Did I try it on a busy system?
Yeah, on a busy system.
I did try it on a busy system, but I learned that I was giving this talk after I got off my airplane instead of before, so I didn't get the numbers. But the numbers on a busy system, the deceleration is less of a problem. If you keep the CPU busy with meaningful work like rendering web pages in the Squid case, for instance, then the acceleration will still be meaningful for you because it's transaction-based. You can keep the CPU busy with real workloads and have the crypto accelerator do your crypto bits for you.
Because some of the trouble we've had with Squid and some not so Squid SSL stuff was that the CPU was quite happy doing, networking and whatever, HTTP parsing and stuff like that. And what we were trying to find was the crypto hardware slower or faster than doing it in line with the work. And for some, I haven't got the numbers, but for some stuff it was, and for some stuff it wasn't, which
synchronization is probably also going to be an issue. You want to keep your CPU busy and you want to keep your crypto hardware busy at the same time, and preferably you want them to meet somewhere at meaningful points.
Do you know if there are any examples of this stuff being done right or not?
I haven't seen any examples of it being done right, but I've got some numbers somewhere at home on a machine locked away, which you might be interested in seeing. I've not tested Squid in particular. But
I wouldn't test Squid, it'd be crap, but...
that's,
well, no, but there are other...
That's Squid for you.
It's getting less crap, honest. There are other things that tie in to do SSL, like SSL offloading, HTTPS offloading, which is why I'm curious about the numbers.
One thing I have found is that the acceleration is particularly beneficial for IPsec. And for SSL appliance sort of systems where you've got, in the case of IPsec, you want to have some machine sitting in the middle doing your VPN tunnel for you. And that's, well, you're not going to waste a very powerful CPU on those devices and mega cooling. So what I've done at home is I've got these Suport devices which have fairly modest CPUs, and they've got this crypto block which just turns the, I don't quite get wire speed IPsec, but I get about 75, 80 megabits on a 100 megabit line.
So that's my next question is so given the slightly different crypto handling across these little chipsets, has anyone come up with a list of what they're good at and what they're not good at? Like, this stuff's good for this kind of SSL. Because just as a bit of background, I've had issues in the past where people have gone and bought crypto hardware acceleration cards, and then certain types of SSL negotiation doesn't work through the card.
Well,
right?
it helps if the hardware supports the encryption schemes you're actually using. Most of these hardware cards only support one or two algorithms. AES is very popular, but well, one of the things you also have to be careful about is that they only support certain key sizes.
Yes.
Yeah.
Certain
So
types of
I think it's in my numbers if I find the page up button here. This is the good example. There's a significant difference between what it feels about 1K blocks and what it feels about 8K blocks. The 8K blocks are rather faster, and also, well, the deceleration is the same thing. The deceleration isn't quite so obvious for the 8K blocks as it is for 1K blocks. So that's one thing to keep in mind is most web servers seem to like variable key sizes, and the clients will go off and tell the web server in this SSL handshake, hi, I support the following algorithms, and I would like to use this key size. And the web server says, oh yeah, that looks fine to me, but well, I've got this hardware here, and I can't do anything with this key size. So asking me 256K keys, and I have hardware for 128K, and it's not going to be intelligent enough to chop them up. So, any other questions? Yes. Microphone. For the records.
You I'd like to know if the crypto algorithms you're using on the CPU, if they've been optimized and compiled to use the vector units on the CPU, like SSC instructions or MX or something like that.
I've not done any sort of test for that, but I assume that, well, I don't know. I have no idea actually. I think crypto is mainly bitwise and bytewise operations rather than blocks.
Yeah, so it strikes me as it would be rather easy to optimize for such vector units.
It would be something to play with if rather than hours on airplanes. Here looks like he's
Just a quick comment on that. In the FreeBSD kernel, we don't do anything with floating point, so
Yeah,
that
well,
stuff is out. So maybe use a LAN to do that.
Yeah.
Kernel, so
Well, I don't want floating points to be kernel. Definitely not suggested.
It was a question about the crypto libraries and using that actually.
Yeah. So yeah, with OpenSSL, it shouldn't be too difficult to teach OpenSSL to do these things. It's just OpenSSL code makes migrating easy.
I've done some work in this space on some of the platforms, and with the vector operations, even in AES, one does get some improvements.
Okay. Do you have any numbers or any test suites or tools which I might want to try out?
Nothing that I can release. Sorry.
Anything you can use?
So just to address that point about OpenSSL. So OpenSSL has assembly language implementations of various things, optimized for various CPU types. We have a statically generated version of that a number of years ago. So because of the way we build OpenSSL using FreeBSD main system, we don't. The OpenSSL builder does this stuff that it runs Perl script over or something. We have a statically generated version of that from a while ago. It should probably be updated to whatever they currently have. I'm sure in recent years they've added more assembly language stuff to that. So it'll be a great project to work on actually.
Yes, the OpenSSL in the FreeBSD tree is currently not quite optimal. When I started working on this summer, I convinced the glory of the OpenSSL project to be punished with a FreeBSD commit bit, and then he broke his wrist to avoid working on FreeBSD. It's probably the most extreme example of avoiding committing I've ever heard of. But once he recovers from that, I expect to put him to work on maintaining OpenSSL. One of the things I definitely want to get in is this automatic engine selection, because in the case of, for instance, Socrates hardware, the difference is quite impressive. If you're doing IPsec, and that's what these Socrates things are for, you want to stick them in front of your network and do IPsec for you. And if they're going to be extremely slow, 10 megabits per second on a 100 megabit line, you don't want that. So if you can get 75 megabits, that's probably as much as you're going to get out of anything on the other end. So, anyone else? Thank you.